All right, so yesterday we finished up on this slide, which summarized the two major types of waves that we're talking about. Transverse waves move up and down. They literally travel through space like a roller coaster like that. The most important type is electromagnetic waves. That's how we get all of our energy from the sun. And that's all of the energy we have on Earth comes from the sun. So they're the most important kind of transverse waves. And then we had 6 types that we talked about. So in order from highest energy and highest frequency, the energy of an electromagnetic wave is determined by its frequency. So highest frequency, meaning how many times it passes a point each second, is the highest energy. And that goes gamma rays, X-rays, ultraviolet, visible light, infrared waves, and radio waves. And then we have longitudinal waves, which we haven't talked about in detail yet, and those would be like sound waves or springs. They move back and forth. So think of a spring being squeezed and released, squeezed and released. That's what a longitudinal wave is. Okay, so let's move on. We're going to talk today about properties of different waves, and maybe one of the most interesting is the superposition of waves. So when two waves occupy the same space, they are said to be superimposed. This is called superposition. So that's one of the unique characteristics of a wave, is two waves can, because they don't have any mass to them or matter to them, they can occupy the same point in space. Think about your fist. If you make two fists out of your hand, those two fists can't occupy the same point in space at the same time. Your right fist can't occupy the space that your left fist is occupying, and vice versa. But waves, because they don't have any matter or any mass, two waves can occupy the same place in space at the same time. So when two waves are superimposed, the amplitudes, the heights of the waves are added. So it looks like this. So you see a red wave and a yellow wave. They're identical to each other. And you notice that the crests of each wave are lined up perfectly. So not only are they identical waves, but they're said to be in phase. So what happens if you laid one of those waves on top of the other? It would look like this dark blue wave. So what happens is you notice that the wavelength and therefore the frequency don't change. But what does change is the amplitude. You literally add the amplitudes of the two waves so that they're taller. The resulting wave is taller. And that's called constructive interference, because it sounds kind of funny to say constructive interference, but they're actually constructing each other. They're building on each other. So the interference just means they occupy the same place at the same time. But they actually build on each other and make a bigger wave with higher amplitude. And these two waves are said to be in phase because their crests exactly line up and their troughs exactly line up. So here I put the waves down at the bottom. So the maximum amplitudes of the two waves here are in the same place, and these waves are said to be in phase. So I put the waves on top of each other, and I get that same blue, dark blue interference pattern, it's called, but it's a new wave formed of the two waves. So that's one of the interesting aspects of waves, that waves can add to each other. The next point is a similar point. It's really the same point, but it's, in a way, a little more interesting. When two waves are out of phase, like these two, they cancel out and result in amplitude that is less than the amplitudes of each of the waves. So if you look at the white dashed line, it's going through the crest of the red wave, but it's going through the trough of the yellow wave. And let's just make up a number. Let's say the amplitude of the red wave is 3. Amplitude of both waves is 3, but where the dashed white line is, the red wave is at a positive amplitude of 3, and the yellow line is at a negative amplitude of 3. So what happens when you add +3 and -3? You end up with 0. So look down there at the bottom. It says when you do that, the waves are added, the result of the amplitude is 0. So you'll notice that down there on that bottom graph, that the line is flat, where those two waves are exactly canceling each other out. And does that mean that if you put two light waves, two beams of light that are out of phase, they'll actually be dark? It'll actually cancel each other out? Yes. You'll actually have a dark spot where those two waves hit the wall. And that's called an interference pattern, and it's a very interesting phenomenon, because you can have one wave of light shine at the wall and you'll see light. You have the second wave of light shine at the wall, you'll see light. But if you put them both together shining at the same place, and they're exactly out of phase like this, you won't see any light. The same thing is true of sound, and I'm going to demonstrate that on a computer program that we'll use next week for a couple of days, either next week or the week after for a couple of days. Pretty sure next week for a couple of days. And you'll see how sound waves can also cancel each other out. So when the waves do cancel each other out, the peak of one wave or the crest of one wave lines up with the trough of a second wave, and they cancel each other out. That's called out of phase. The waves are said to be out of phase. All right, refraction. So we're dealing with different properties of water in today's lesson. And just as you can run faster in air than you can in water, a light wave moves faster through air than water. When a light wave going through the air hits water, the side that hits the side of the wave that hits the water first will slow down. Think of it like if you're in a car and a car is driving near a beach, and suddenly one wheel of the car goes into the sand. Suddenly that side of the car will be slowed down, and what the car will do is turn into the sand because it's being swung around because one side of it's going slower than the other. The same happens with a light wave. When a light wave comes at an angle, the side that hits the water first slows down. That means the other side is still going faster because it's going through air, and so it turns, just like that car with one wheel hitting the sand. And the light wave will turn. So this causes the wave to bend in that direction. When light bends because of a change in medium, so air is a medium, water is a medium, but water is, you could say, thicker, more dense, it's called refraction. So if you've ever noticed this phenomenon you see in the picture where the straw looks like it's broken, that's because of refraction coming through the glass, coming through the water and then through the glass of the glass there. Okay. Diffraction's a little bit different. When light passes through an opening, it bends by a process called diffraction. And the longer the wavelength is compared to the width of the opening, the greater the diffraction. So you can see both kind of just a diagram there on the right of diffraction, but you can also see it actually happening. That's actually a laser light going through a small slit, and you can see that the light spreads out, and that's called diffraction. What is polarization? Polarization means that only waves oriented in a certain direction can pass through a barrier. Glass can be polarized so that only some of the light can pass through. So if I send a wavelength, remember, light goes kind of like a roller coaster up and down. So if I send an up and down beam of light, or wave of light, excuse me, and then I send one sideways, so it's simply the same wave of light, but it's turned to the side. If that rectangle there represents polarization, it's like it has slits in it that are up and down. Imagine that you can't see them from the side, but it has slits in it that go up and down. Then the up and down wave will go through because it can pass through, but the sideways wave will not. The way I liken it is, think of a couch going through a door. So maybe you call it a sofa in your house, but one of those big long things you sit on, a sofa or a couch. If you try to carry it out of the door sideways in its normal orientation, the way it sits on the floor, you can't do it because the door is not wide enough. You can't fit the couch out. But if you're moving and you need to get it out, you turn it up on its side, so it's side to side from top to bottom, and now you can fit it through the door. And that's kind of what's going on here with polarization of light. Okay, what are sound waves? Sound waves. As sound comes out of a speaker, it produces a longitudinal wave. So this is the compression or slinky type of wave that causes air molecules to press together, then be released in alternating high pressure, low pressure areas. This is the same pattern as a spring. So when I talk, what my vocal cords inside my throat do is they wiggle the air molecules right next to them. And those air molecules don't fly out of my mouth and go and hit you in the ear. That would be like me throwing a ball to you. I would toss it from me, the ball would go through space and come to you and then release its energy when it got to you. That's not what's happening here. What's happening is the air molecules in my vocal cords are wiggling, and then they're going to wiggle the next air molecules next to them, and then those will wiggle the next air molecules next to them, and that'll keep going until they wiggle the air molecules in your ear that are right next to your eardrum. And those air molecules will wiggle your eardrum, and that will send nerve impulses to your brain to give you the sensation of sound. So it's not the air molecules in my throat that go and hit you in the ear. If that was true, my voice would only be able to travel in one direction. The fact is, you could be standing behind me and hear me talking, and that's because my voice comes out and it goes in all directions. Goes out in all directions, and then it eventually gets to the air molecules that are in your ear. It wiggles those, they wiggle your eardrum, and then you can hear. So this is just kind of a representation. So the areas of high air pressure are where the little dots are clustered tightly together, and the areas of low air pressure are where there's not very many dots. Now, what do you think? Which causes you to hear sound? When it's high air pressure or low air pressure? Low air pressure means lower than the normal air pressure in the room. And the answer is both cause sound. So when the higher pressure hits your eardrum, then it pushes your eardrum in, and that creates a sensation. But when there's low pressure, lower than the room's air pressure, it'll pull your eardrum out. It's like it's sucking it out, and that also moves your eardrum. So both high and low pressure cause your eardrum to move. It's when there's no air pressure that's different than the normal air pressure of the room. That's when you don't hear any sound. Okay, the Doppler effect. So a moving train sounds its horn. The train is moving into the sound wave that goes out in front of the train. This squeezes the wave in front of the train. The train runs away from the sound wave going out the back of the train. This stretches the sound wave. So a shorter wavelength is going to be a higher frequency, and that produces a higher pitch. A longer wavelength produces a lower frequency, that produces a lower pitch. So you can see what's happening is the sound is going out in all directions. It's not just going forward and backward from the train, but we're just trying to keep it simple. So as the sound goes out in front of the train is chasing after those sound waves, so they basically shortens the wavelength. So they sound higher pitched. Whereas the sound coming out the back of the train's running away from those sound waves, and so they're stretched out. They have a longer wavelength and a lower frequency, and therefore they are lower pitched. So I'm going to show you a quick video example of this. Okay, so that gave you an example of the Doppler effect. What are beats? Beats are when two sounds of different frequencies are heard together. The sounds alternate between loud and quiet. Sound waves can be added to one another and can subtract from one another just as transverse waves do. So if you look at this diagram, you can see two sound waves that have different wavelengths and therefore different frequencies. So on the left side, you see that the high air pressure of the two waves is occurring at the same time, so that would be loud. Then next to that, you see the high air pressure of the top wave lining up with the low air pressure, and they cancel each other out, just like we saw with the superposition effect. So that's where it's quiet. Then the next one over is low air pressure matching up with low air pressure, and that would be loud again, because that's pulling out on your eardrum. The air pressure is low, and it suctions your eardrum out, and that creates a sensation of sound. Then the next one is the low air pressure on the top and high air pressure on the bottom, and that would be quiet because the two waves cancel each other out. High and low cancel each other out. Next is loud because it's low pressure, and finally loud where it's high pressure. So again, when you have it loud, that's constructive interference, and when it's quiet, that's destructive interference. However, in both cases, your ear gets the sensation of sound because your eardrum is moving. Okay, so here's a simple math equation dealing with beats, and it's computed as follows. The frequency of the beat is the frequency of one of the sound waves minus the frequency of the other, and the absolute value symbol means that the answer is always positive. So what is the beat frequency of a 340 hertz and 360 hertz wave? So 340 minus 360 is negative 20, but you take the absolute value of that, that just makes it 20. Same down below. 400 hertz and 250 hertz wave, you just subtract, you get 150 hertz for the beat frequency. So let's listen to an example on a video of beat frequency, and that will wrap up this lesson. Okay, so that concludes our introduction to waves this week. A lot of the terminology, there's not a lot of math equations to it, but to know the terminology. Next week we'll get into some projects that are kind of interesting with waves using some software, and I'll show you what the software is and how to download it if you want. It's not required for the class, but you can do that if you would like. I would like everyone to attend the Tuesday meetings, at least to check in. Okay, so I hope to see you all at the meeting tomorrow. Just check in. I'm required to have a contact with you every week. It could be submitting an assignment. It could be the Zoom meeting. But I would like everybody to just check in at the Zoom meeting, just so I know you're still out there, and you know, stay on for 5 or 10 minutes. We can just chat a little bit, and then you're free to go. Unless you have questions, then you can stay. Okay, so take care of yourself, take care of your families, and be well. And I'll talk to you next at the Zoom meeting tomorrow, and then later this week if you have any issues to resolve. Thank you. Have a good weekend. Have a good week.